z maps to uz, right? The only point which maps to itself is the origin itself. Every other point is moved. Unless, of course, unless u is identically 1, in which case the whole thing is, every point is fixed. So, all right. So now he's going to move on to try to explain how Quaternions give us a way of implementing rotations in R3. Now, I tried to do this in number theory, but I got hung up on the details. They're a little bit subtle. And well, we're going to try. This may be, if it goes sideways, it'll become a homework problem. So let's try to get it done. Yeah. All right, so we got that.
It's 5 o'clock p.m.
Let's see here. So the Quaternions, they've got I usually think of t as being time and the other piece as being space. I mean, Hamilton was actually thinking of it that way. He's seen this, at least for these metaphysical ideas about it being space-time and things. I mean, that was part of it. Part of its attraction to people too, physical meaning. Anyway, so he says a pure imaginary quaternion, it basically is of the form, more trouble with markers. P is equal to, something like AI plus BJ plus CK, right? This is a pure imaginary quaternion. Make sense? I mean, that makes sense, yeah. In other words, it only has a vector part, right? So the set of all such things forms a three-dimensional space. It's basically in this, right? IR, JR, KR, right? Now, on the other hand, if it has the form, if P was just equal to, say, 1 times A, that would just be an element of just, well, I guess you could say 1R, but sometimes we omit the, I've erased it, I don't know if I wrote it or not. I usually just write R plus IR. The 1 is understood. Sometimes I would just say that this is equal to R, but, I mean, the point is, Quaternions are the direct sum. Oh, why did I hate it that I erased that. Quaternions are this, the pure real Quaternions direct sum this other thing, right? What does it take for it to be a direct sum? First of all, two spaces are direct. If we were talking about two spaces, right? The total space is formed from adding together things in here and things in here. Essentially, that's the definition. And also, the intersection is 0. That suffices for two subspaces. And of course, the intersection is 0 because, you can't have nothing in here is also in here unless it's the 0 vector. So it is in fact a direct sum. All right. So here's what he going forward with the discussion. He's like, okay, so if you take two members of these pure imaginary quaternions and you multiply them, what happens? Is the set of imaginary quaternions closed under multiplication, under just products?
Didn't we already see? There's just the cross product, right?
Right. Well, the cross product is what we want. That's another vector piece, right? Mm-hmm. But this right here means multiplication of, IR plus JR plus KR with itself not closed, right? It goes outside the space. You pick up that dot product, right? So that's not going to form a group of things, right? Right. But he extracts a little bit more out of this formula that I just circled in red. He's like, all right, so the product of U and the product of V and W is real only if what? Just trying to collect my thoughts here. Let's see here, so U. I'm sorry, I use V and W. I use V and W. V W real if and only if what?
V dot W 0.
All right. Right.
Well, no,
Oh.
real if V cross
V
W
cross
0.
Yeah, I'm sorry.
Jumping ahead.
And VW pure imaginary. Now we got the. Now, what does it mean for the cross product of two vectors to be zero geometrically?
Parallel.
Right, they're collinear. They're either in the same or opposite directions, right? Now, so then, what if we focus our attention then on U and I don't know if I want to do. Sorry. Yeah. U and the pure, U, pure imaginary one. Okay, so.
Do we have a good abbreviation for pure imaginary or no?
I don't at the moment.
I was gonna say PI, but then I can get the I actually.
You guys can call it. I mean, you can call it whatever you want.
The P with the double lines I.
You call it Vec H. I don't know. I'm sure that's something else, but call it or I don't know. How about H?
H minus R.
I don't know. Anyway, the point is, if you consider U in here, and silly notational choices aside, the absolute value is 1. Then what does it say? What do we say then? What do you say about U squared? What's U squared is equal to what? Notice. So I was using, I mean, my notation is just to put a vector over it. I mean, U is in here if U is equal to U vector. In my notation. E uses this notation too, but so U squared is what? It's U, right? It's U dot U, right? Plus U cross U.
Which is 0.
Right.
Which is minus.
So if that's equal to 1,
It's U dot U is minus.
right.
Where did the minus and the original dot product come from? U equals negative U dot U.
And
Oh, yeah. Okay.
I'm not sure why that whole thing is equal to 1.
Isn't the absolute value of all of them? Well, if the absolute value of U is 1, then U squared is 1 too.
Oh, right. This
Yeah.
this is minus 1.
Yeah,
I'm
minus
sorry.
1.
That's minus 1.
Okay.
Definitely that's minus 1. Okay, and that comes from this assumption. This says that I mean, the quaternionic absolute value is just the dot product of the vector with itself. It's just ordinary length of vector because there's no.
Right. Just you get up there, all that.
Yeah.
Okay.
He says, thus every unit vector in the pure imaginary quaternions, lacking a better name, is a quote-unquote square root of -1. Every, and like how many of them are there? There's a lot. I mean, it's not just, certainly it's just not just two things, right? But you notice we have here, we have the equation u squared plus 1 equals 0. It's a quadratic equation. I mean, if this were a complex variable, we know there'd be two solutions. The fact that it's a quaternionic variable. See, quaternionic, it's a polynomial quaternionic equation of order 2. It has infinitely many solutions.
Really?
Yeah. Because every unit quaternion is a solution. So what we're about to explain is how that corresponds to rotations in 3 dimensions. Not directly by multiplication. There's kind of a sneaky thing that happens here. All right. So he says a quaternion T of absolute value 1, like a complex number of absolute value 1, has a real part and an imaginary part. All right. So now he's no longer just looking at these. Now he's going to look at the larger space of all quaternions of absolute value 1. Okay. The so-called unit quaternions, or I guess you could call them unimodular or something. I don't know. All right, I'm going to foolishly erase this. I will soon discover why I need it still. Let's hope not. Okay, so I got to come up with a better system for these markers. Just let them dry out, I guess. So let U, I'm sorry, I guess he said T. T be an element of H with, he says then there exists cosine theta, well, let's say there exists a theta in the reals, all right, such that T is equal to cosine theta plus some U, I'll put a vector on it, sine theta, where the space without a name. All right. Okay. Now, hey, that is exactly why I need to flip this room. All right, so where are we?
But then you'd be the one seeing it. In this situation, at least.
I don't see anything when I'm over there. I just be looking at the board, oblivious from the world. Okay, I'm sorry. Getting to the point here. Why are we looking at this? He says the real part is the cosine theta. The imaginary part has an absolute, quote-unquote imaginary part, has an absolute value of sine theta. He points out that u squared is equal to -1 by the calculation down here in the red. U vector, right? I guess I'll drop the vector if that's okay. You can put a vector on that. I mean, it's all right. Now the point is, by analogy, we saw how multiplying a complex number, right? If we multiply a complex number of this form, right, of length 1 on a complex number, then we got a rotation, right? Well, we got an isometry, right? How about this? What happens if you multiply a quaternion by something like this? What happens then? Right? Now, but we're not actually, we're really interested in R3, right? So we're hoping that we can identify R3 with these guys, right? And we want to see how quaternions give us rotations of these. So what happens if I do something like t, times something like this? Do we again get something in quote-unquote R3?
It's still going to be pure imaginary.
But is it?
Is it? I think so.
Not necessarily. I guess U and AI plus BJ plus CK have to have dot product 0. Or no, I guess
Yeah,
not
what is the U again?
See, U is pretty much an arbitrary element. I mean, this U,
Is U in the pure imaginaries? Just some element of that?
U is something like U1I plus U2J plus U3K. I mean, you can see that when you multiply that, you're going to pick up a real part,
Right, so unless U is 0, then you're going to have a real somewhere.
right?
Okay.
So this won't work. This won't work. It's why multiplication by a quaternion of length 1 doesn't produce a rotation in R3.
Oh, man.
I know, right?
That'd be useful.
But what he points out here, though, is that that doesn't do it. What you end up needing to look at is conjugation. So his claim is if we look at something like T inverse, and I need a name for this point, let's call it, I'll follow him and call it Q. So if you look at T inverse QT, like this, something about conjugating ends up killing off the real part. Like one multiplication creates a real part, the other multiplication destroys it. And you're again an element of IR plus JR plus KR, right? And furthermore, if you work out the details of that, it ends up basically taking this point Q and rotating it by twice theta around the U axis. It actually uses U as the axis of rotation, and it multiplies by twice theta. That's
That way you don't need two angles. You just use U as the axis.
yeah, use the axis, and theta is the rotation angle around. And Euler's theorem says that any rotation in 3 dimensions can be written as a rotation about a particular axis about a particular angle.
Mm-hmm. So how do we know what the distance is in that one? Is it just 1 always? Because
and see, in this, so page 14 and 15, this is probably logical. I don't quite understand this argument yet. I want to understand this better, honestly. I can show you why this gives you an isometry. I can prove it gives us an isometry without much work. That part is easy. I'll do that now. So why is this an isometry in this space? All right. So let's look at 2 points in R3. Let's conjugate them by such a unit quaternion and see why we get the same distance between points. Let's see here. So again, I want to take 2 points. Let's say, I'll say P1 and P2 in R3, which we're viewing as IR plus JR plus KR, right? And what we want to do is we want to map these, T inverse P1T and T inverse P2T, right? So we're conjugating these points by this unit quaternion. That's what he claims produces an isometry of R3. Let's see why. So what's the trying to remember. Oh, we know that the quaternionic absolute value is multiplicative. That's the critical thing here. So we have to look at T inverse P1T minus T inverse P2T. I think you see where this is going. Use the multiplicative property of the, factor out, right? So this is really, let's go.
You can do that?
Yeah, that's a good question. Can I factor? Well, both. I think I could factor, right? That's T inverse. Am I wrong?
I guess so.
I think it's distributed.
They are in the same order, yeah.
I mean, that's just the distributive property, right? Yeah. And then, well, I mean, I can do it again, right? That's just algebra. Now I can use the multiplicativity of the norm, not norm, of the absolute value twice, right? And that gives me but we know that the modulus of t, we know the modulus of t is equal to 1, right? So the modulus of t, I mean, the absolute value of t is 1 by assumption. By assumption is 1. Because, I mean, that was up here.
No, when you're saying modulus, I was going back to proofs and thinking
I know, I'm sorry, I don't mean, yeah, I know, we're generalizing, we need to use a different word or something. But of course this means is 1, right? So that means that, well, I guess there's still something to prove. How do I know that this is equal to the modulus of 1 over t, right? But if I know that, right, that's equal to what?
So we can say, and then T inverse.
Right, so bottom line is that this is, so the distance between points in this space without a name, let's call it R3, is preserved, right? So conjugation by a unit quaternion, honest to goodness isometry, and it's also fairly clear that it only fixes the origin, which gives us reason to think it's a rotation, R3. Now, the reason that rotations in R3 are identified with isometries is a different discussion. It's actually somewhat involved. If you want to see that, it's in the differential geometry course towards the start. I spend like a lecture on it. You can just start with an abstract isometry and prove that they have to be linear, basically. And then, well, you prove that they have to be affine, I think, right? So they're either rotations or they're translations. But the translations leave no point fixed. So if it fixes the origin, that means it has to be a rotation. That's the logic behind here. He's referencing a discussion about isometries from another course when he talks about these things. Now, the thing I'd like to do better, that I'm not going to do today, is this claim that it's a rotation by twice the angle about that axis. I want to understand that better than I do right now. He's got 2 pages of calculations, but I just...
What do you mean by twice the angle? Like 2 theta?
Right, it's a rotation by 2 theta.
Okay.
Now, if you look at like Wikipedia page and stuff for the Quaternions, you'll see that, you know, they just pull this form. I mean, they probably has derivation there, but I never give them any money, so I kind of feel guilty to go look at it. Not really.
Finally, almost at the point where I can look at a Wikipedia page and it means something when I look at it. 'Cause all my life, I've stayed away from the Wikipedia pages on math. You go into way too much stuff.
Yeah, there are definitely some nerd battles in the in the Wikipedia. That is true. But anyway, thank you for bearing with me, guys. I will try not to talk too much about Quaternions next time. We'll try to move on to chapter 2.
You should talk
So-
about Quaternions more.
I'll see you next week.
Maybe see me next week.
Yeah.
Unless you